actually present these topics around OpenMP. Okay. So by the way, if at any point in the presentation you have any questions, please let me know. Okay. I think it would be good if it is like interactive. By the way, I don't know if you see any blocks like this type of black boxes that I see here on my screen because of the controls of Zoom. If you see them, I can try to probably move them around so that they don't disturb. Okay, let's start with that. So I just observed that you were actually doing a little bit of OpenMP. So I understand that this tasking approach joins perfectly with the session that you have had. So as you have probably seen, OpenMP traditionally works with the fork join model. So this covers most of the work sharing primitives like fork, sections, and single. And now we will introduce tasking, which is a different approach for parallelism, but it is actually integrated perfectly with the, let me get one of these pointers. It integrates perfectly with the fork join model. Okay. So with tasking, parallel regions are created with a parallel directive. So you do the same. And although it is a little bit strange, inside the parallel you put a single, you use single in order to have a single creator for the tasking. The single creator creates the tasks and any other threads in the parallel team executes them. And when the creator actually stops creating because there is no more work to create, so it reaches the end of the single section, then that thread also goes to execute additional tasks. So the data environment is very similar to the fork join approach. We will see some examples, except that task variables are first private by default. So any variable accessed by the task by default is first private, which makes sense because probably the task wants to actually inherit the value of that variable from outside and then be able to modify without any raise condition. But we can actually change the meaning, change the data sharing of the variables in order for them to be private and shared. So this is actually the two graphs that I prefer to show at the very beginning. So let me see if I can move this. Maybe here. Okay. So at the top, the traditional fork join, okay, where you have the sequential flow that spawns. This is a fork on 4 threads. There is a master thread. There are the worker threads. There is the end of the first parallel region. Then you spawn 2 threads here. So it's a fork of 2 threads with an additional inner parallel region of additional 4 threads that joins here. Then everything is joined. This is the end of the second parallel region. And then we have a third parallel region. Usually, if we implement a similar approach with tasking, you have a fork place where you start creating. This would be a single, just creating the rest of the tasks that are executed here. Okay, these green boxes. Then you have the end of the parallel region. You can actually mix. Some threads can do actually a parallel region, and other threads can be executing tasks. Okay, so everything is kind of mixed. And here you have another region where probably there is not enough work to do, and one or maybe even 2 of the threads at the end doesn't have work to do. So this causes a little bit of imbalance. Also to show some of the drawbacks of tasking that may increase the imbalance if you don't take much care of the scheduling of the tasks in the threads. Okay, so let's start with the basics. So we can define a task as a work unit, okay? And as such work unit, its execution may be deferred. So it's not executed immediately, but it is deferred for a later execution. Of course, you can only do that if the task is actually parallel regarding to the other work that is actually present in the application, either in the same thread or with respect to the other threads. Actually, OpenMP also provides the means to execute the task immediately. Okay, so they appeared in the OpenMP 3.0 specification. So that was 2008. And tasks are composed of the code, which is probably a section of code to be executed. Usually it's embedded in brackets and annotated with the pragma task, which includes the set of instructions, any function calls, additional functions that the task may call, any library functions that the task may also call. So it's free to execute any set of code. A data environment initialized at the task creation time, and some internal control variables that may include how many threads are available for the task to spawn additional parallelism, or its priority, for example. Okay, so the typical internal control variables of OpenMP. In OpenMP, tasks are created when? So the first thing is when reaching a parallel region. So at this point, actually, here at this point, we have the creation of some implicit, what we call implicit tasks, okay, which would be the threads that are below the execution. Okay, so this green thing is an explicit task, but the executor is actually an implicit task. Okay, and I have also to note that I'm using here gray or light blue color, okay, instead of the more dark blue color, okay, when this is actually something that it's not actually related to the tasking itself. It's something that is more on the basis of OpenMP, okay, or related to word sharing, or related to parts of OpenMP that are not specifically related to tasking. So the second point is when encounters a task construct. Okay, we have not seen yet the directive, but there is a directive. OMP, pragma, so pragma OMP task. Okay, so when an explicit task is created. So see the difference between implicit and explicit. When encounters a task loop construct, we have a special loop, parallel loop, which we call a task loop, which is a loop implemented on tasking. Okay, so then explicit task per chunk is created. And when it encounters a target construct. So this is also interesting. If you use GPUs, devices with OpenMP, any target device construct that you have, it's also implemented as a task, which allows also to include for instance, the task dependencies across target constructs. Okay, so the good thing for tasking is that they support parallelism that was not supported with usual work sharings. For example, you can support unbounded loops. You can do a while and create tasks in between. Okay, tasks in the while will be actually going to the task pool, and they will be executed by the other threads, thus achieving parallelism. You can also do tasking on recursive function calls. So if you actually annotate my code as a task, then every invocation of my code will actually create a task. Okay, and it will act in the same way. So several scenarios additionally are possible. So in this case, we will have a single creator, but it is possible to have multiple creators if the tasks happen to be in a parallel region with no single. Okay, and all members in the team are candidates to execute these tasks. So if you have this team of threads created by a parallel with 4 threads, all of those are able to execute the tasks that are created in the task pool. Okay, so the task construct, this is probably the most important slide, no? So we have the directive, pragma, OMP, task with a few clauses. And here we put brackets for the structure block. Okay, so the section of code that we have. In Fortran, we don't have the brackets, so we need to say always OMP task and OMP end task. Okay, so we have both directives, the starting point and the ending point, which is in C. As we have the brackets, we just use the brackets to do that. So as before, what is more gray is the clauses that we have already seen in OpenMP. No? Variables in tasks can be private, first private, or shared. And you provide here the list of variables. You can also say default shared, which means all variables will be shared. Okay, so all will be managed as if appearing in a shared clause. Or you can say default known, which is actually very interesting because in this case, the compiler will complain if a variable used by the task is not actually in one of the private, first private, or shared clauses. Okay, so this way you ensure that as a programmer you will specify the behavior of the task of the variables as you want. Okay, and if you missed anything, the compiler will tell you, hey, we need also to express this one. And then we have untied, if, mergeable, final, priority, and depend. Okay, those are the additional clauses that we have for tasking that we will see across the lesson. Okay, so let's talk about the data environment. We have a predetermined data sharing attributes, which are perfectly matching the usual OpenMP. In a task, thread private variables keep being thread private. Any malloc new memory keeps being shared because we cannot privatize that. We don't know the size, so it would not be possible to privatize that memory. Static data members in an object in C++ are shared. Variables declared inside the construct. They have static storage if they are, so if they have a static storage, they will be shared. If they have automatic storage, they will be private. And the loop iteration variables are privatized as usual. So we have some explicit data sharing clauses. This is actually what I was explaining in the previous slide, no? Shared private and first private, and the default, including default known. And then we have some implicit data sharing rules for the task. This is explicit for the task. This is why it's not gray. It's the new concept. So the shared attribute is lexically inherited. So if a variable is shared above the task, it is lexically inherited. So this means that it will keep being shared. And in any other case, the variable will be first private. So here I have an example in which we can play a little bit. No? So we have a global variable A, a parameter B, a local variable for the function C, and then we start a parallel. Okay, parallel private C, and then inside the parallel we have a variable D. Okay, and a task, and we don't have any clauses here. Okay, even we don't have a default known, so we should be able to try to see what happens with these variables. Okay. So I will explain a little bit what happens, and then we will see an example. We will see actually the code as it runs. So what happens to A? A is actually global. Okay. So in the case there is no additional directive, for task it will be first private. Okay, but be careful here because lexically we have this parallel region here. What happens to a global variable in a parallel directive? That it becomes shared, because in parallel, the default is shared, and we are not saying anything here about A. So if this directive here transforms A to shared, it will keep shared in the task. So if I assign a value to A, that variable will take the value that it gets in the expression, and it will be assigned into A because it is shared. Okay. So what happens to B? For B it happens the same. It goes across the boundary of the parallel, so it will become shared. So it will be shared. What happens to C? C, it's going also to the boundary of the parallel, but it is explicitly referred here as private. Okay, so if this is a private variable, I should check that, but I think for task it will be first private because it is not shared. Okay, Actually, we should check that because I'm not sure. D is only a variable inside the parallel. Okay, so it will be private in the parallel and first private onto the task. And E is only private onto the task. Okay, and then I realized that in this example, we have here G, which is actually an error, right? Because G is not actually declared. Okay, so let me see if I can find my other screen here. This one, where we can see the different topics that I was explaining. So I enter data sharing. I have here the same program, except that I have initialized the variables. A takes the value 0. B actually takes the value 1 when I invoke foo. Okay. C takes the value 2. Okay. And then I don't initialize D, by the way, but I don't think we print D. So then inside the task, I'm trying to assign, instead of 0, 1, and 2, 10, 11, and 12. Okay, and then D becomes 13, and E is local, so we cannot say anything about that. So let's say what happens after the parallel region. Okay, so if A has changed the value, this means that this A has been shared inside the task. If B has changed the value, the same, no? It has been shared inside the task. And also for C. C will probably not change the value because it is actually private in the region. Okay, and then here we have foo of 1, which is the parameter B, and another printf for A, just to be sure that everything goes well. So I can do make run, and we see that A and B are shared, and C is private, okay, because C has not been modified. So let me just do what I was thinking. I should actually, it should be possible to say that D is 3, 0, 1, 2, 3, and then do something like, I'm going to wait for the pragma OMP task wait, and I'm going to print D. D is an integer. So I initialize D to 3. I execute the task, and I make sure that the task has been executed. If D is shared for some reason, it will become 3. It will become 13, sorry. Okay. If not, it will be remaining as private. My idea is that D here will be first private. So actually it will be not modified. So I can do make run. Sorry. Print is actually printf. The rest I think is okay. Make run. Okay, so you see that D is actually not modified. It becomes 3, and actually we had like a surprise, no? Because this print appears twice. Why it appears twice? Because it is actually inside the parallel region, so it is executed by 2 threads. Okay. Why it is executed by 2 threads? Okay, observe what I'm doing with make run. I compile the application, gcc -f OpenMP. Okay, so this is to enable the compilation of OpenMP directives, and then I execute with 2 threads. Okay, so this is why this print appears twice. Okay, but it shows that the task actually doesn't modify the value. Okay, so I think with this we have a good understanding of the data sharings. By the way, if at any point you have any questions, please let me know. Okay, if not, I keep running with the presentation. Let's see if I can go to the next slide. That's interesting. We have the solution here. I is shared, global shared, B is shared, local shared, because they go through the boundary of the parallel. C is first private. It's private here, first private on the task. D is first private because it's private in the parallel. E is private because it is private in the task. Cannot be anything else. E. Okay. And for some reason there is no reference to G, which is actually an error. Okay. So let's talk a little bit about task scheduling. Okay, and specifically the topic is between what we call tied and untied tasks. Tasks by default, actually because we didn't want to break any of the compatibility with work sharing constructs, and this thing made us to try to avoid that tasks can switch threads, because there are a number of things that get broken if we move a task from one thread to the other, which is something that was not happening in the plain OpenMP with parallel for or parallel sections. When you have a parallel for, the iteration that is started in a thread ends in that thread. It doesn't move. Okay. So in order to do that, the idea was, well, let's have OpenMP in a mode that is pretty compatible with the previous OpenMP. So in that case, it was OpenMP 3.0 should be compatible with OpenMP 2.5, okay, the former version. But let's also try to make the scheduling a little relaxed in case we can gain something, and also in case that the programmer is aware that there may be some problems with the tasks. Okay, so by default, everything is tied. And this means that any task is executed always on the same thread. Okay, not necessarily the creator, as we have seen, no? The creator is one thread, and then the task goes and it is executed in another thread. But tied tasks may run into performance problems because they are tied. So if that thread is actually executing another thing, this task will not be resumed, and this may delay other portions of the application. So programmers may specify tasks to be untied and relax the scheduling this way, using the task untied clause. With any other clauses additional, no? You can use shared, private, first private, untied, and we will see that we can use others, if, mergeable, etc. Okay, the syntax is pretty the same, except that you add the untied. This means that the tasks can potentially switch to any thread of the team. Okay, will not go to a thread of another team if there is another set of tasks running in parallel, but it will move between the threads of the team. But this doesn't mix well with what we call the thread-based features, like if the task gets the thread ID and the OMP num thread, no? OMP thread num. I do myself equals OMP thread num. And then the tasks go to sleep and gets resumed in another thread. What happens? That the thread num is no longer variable, no longer valid. Okay, my variable, myself, is wrong, indicating the wrong thread. Also, it doesn't work well with thread private, because now I'm in another thread, so I will have different values on the thread private variables. Also, in critical regions, we may get confused about who is the owner of the critical region. Okay, so it's better not to use those properties if you plan to do untied tasks. Okay, the good thing is that it gives the runtime more flexibility to execute tasks. So to see a little bit more an example, this is important, the tight or untightness tasks is important in the task scheduling points, okay? We have task scheduling points where the task can be suspended and resumed at these points. We have some additional constraints to the deadlock problems. But the thing is that we have a set of implicit scheduling points, which is task creation, is a scheduling point. Because at the task creation, the runtime can decide either to follow the code that was there or start executing the new task. Okay, so it's a scheduling point. Asynchronization, getting a log, entering or leaving a critical section is also a task scheduling point. Okay, and we have one explicit scheduling point with this special directive that is the task yield directive. Okay, so OMP task yield. So we can see an example here. We have a parallel single with one task, so it's only one task. Okay, that can be labeled as untied, and then it executes function foo, it does a task yield, and it executes a function bar. Okay, if that untied is not there, so if the task is tied, we are sure that foo and bar execute in the same thread. Okay, but if we have the untied clause, it may happen that the second instance, the second part of the task bar, after the task yield is saying, hey, this is a scheduling point. So the runtime may decide to change the function to another thread. Okay, so this is this flexibility. So be careful if you use untied, because you should actually not use the other primitives, getting thread ID and do some work based on the thread ID, or do not use thread private, and be careful with the critical regions. Okay, a little bit of more controlling task scheduling, and this is achieved with the if, with the condition clause. Okay, so this allows to optimize task creation and execution, especially for very small tasks. Okay, so if you have a very small task or a task that can actually change its size depending on the particular point where it is executed, or on the conditions, or on the input size, or these kind of things, then you can use this if expression. So this means that this is a task if the expression is true. Okay, so if the task is very fine-grained, it will introduce a lot of overhead, especially if we have a lot of them. No? If you have this in a loop and tasks are of 1 microsecond, better not to use tasking for 1 microsecond tasks. So in that case, if the expression of the if clause evaluates to false, then the encountering task is suspended, which means that the thread actually is not executing the code anymore, but it goes and executes the task. The new task is executed immediately, like in this case here. Okay, and the parent task resumes when the task finishes. Okay, so it's just executed and the parent resumes. This is known as an undeferred task. It's a task that is not deferred. Okay, and we will have more data combined with the mergeable, which is coming here. So in the case of mergeable clause, allows to optimize task creation and execution combined with the if clause. Under certain circumstances, it may avoid the whole task overhead. Okay, so here you say task is mergeable if there is this expression is true. Okay, if clause evaluates to false, the task is executed immediately. Okay, so it's actually merged. But actually, in this case, we keep creating the data environment. Okay, which is good for some reasons, no? Because maybe you are accessing some of the variables and you actually want them from the task. Okay, so combine it with the semantic sorry, Combined with the semantics of the mergeable clause, a task for which the data environment, inclusive of the internal control variables, may be the same as that of its generating task region. Okay, so the user agrees, if possible, on relaxing the previous restriction. This means that this mergeable task will actually have their ICVs. So undeferred, so a task that is not deferred and mergeable may execute as a function call. Okay, so that would be, in this case, just execute the function as the task as a function call. But it will never be possible when there are private variables. Okay, if there are private variables, then the task will not actually be executed as a function call because it will lose the semantics. Okay. Very good. And then we have also another control of the task scheduling, which is the final clause. Okay. This allows to omit future task creation. It's not for the current task. The current task is still created, but any descendant task will not be created. Okay. And this allows to reduce parallelism and also overhead. So we can say pragma OMP task final. Okay. And an expression. If the final expression evaluates to true, the new task is created and executed normally, but in this context, no new tasks will be created. And this is seen in this example, okay? So here you have an outer task, which is indicated with a final, that contains 2 additional tasks and possibly a task weight here. Children tasks may have additional task constructs. So actually, there may be additional task constructs in the children, okay? But if final E is false, then you create, the runtime creates all the tasks hierarchy. Here you see B and C, and you also see that C has C.1 and C.2, okay? Not seen in the example, in the code, let's say, okay? But if final is true, then A executes the code as if there were no task directives. Okay, so it's just executing one code after the other. Okay, so you see the difference between final being false, where you execute you unplug, you unfold all the graph, compared to when final is true, when there is no additional task creation. So you save the overhead. Again, you can do that, for instance, checking the size of some input data. No? If the data to process is 1 megabyte, then I don't want to be final. If the data to process is less than 1 megabyte, then I just take the code myself, and I don't create parallelism because I know that it will not be useful. The overhead will be too much. Okay. Very good. So another thing that we have associated to tasks is the priority. Okay. So at some point in the committee, we thought that it could be interesting to allow programmers to actually let the runtime system know the priority that a task has. Okay. We did some experimentation with some applications. For instance, I remember doing that with Cholesky, which is an irregular application. And we were gaining some performance just because with the priority you indicate which are the which are the tasks that are actually in the critical path. Those tasks that actually after those you have a lot of parallelism. Okay, so executing those tasks before, if possible, it allows the runtime system to actually find more parallelism afterwards. Okay, so we provide here a value which is the higher the highest priority. Okay, so will be tried to be scheduled earlier. Actually, the tasks are then marked with this additional priority. Already tasks are inserted in an ordered ready queue in this case. So the ready queue or the task pool keeps the ordering. And once a thread becomes idle, gets one of the highest priority tasks. By default, all priorities are 0, I think. Okay, so here you can say priority 1 or priority 100. Okay, so in this case, you will start creating here tasks of priority 1. Probably some of them will start execution, but as soon as you create this one, the next task to be executed will be the one with the 100, no? The one that is higher priority. Okay, so try that in your applications and see if you can get a little bit more of performance because of the better scheduling in that case. So let's talk a little bit about task synchronization. Okay, so how we can synchronize the execution of tasks. Again, some topics that are, let's say, common with the work sharings. Threads need some order in the sequence of their actions, execute in a logical order certain regions, mutual exclusion in the execution of a given region, so you can do critical or atomic, wait in a location until all the threads have reached the same location, that would be like a barrier, or wait until a given condition is accomplished. Okay. So in OpenMP, we provide different synchronization mechanisms. We have the master construct, similar to single, but only executed in the master. We have the critical construct that allows only one thread to actually enter the critical. We have the barrier directive, okay, in which we stop the execution until some previous work has finished. In that case, we will stop the execution until all tasks have been finished. The atomic construct to do synchronization on small variables. The task wait directive, which allows us to just wait for the tasks in the immediate level. And the task group construct that allows us to wait for all the tasks in the set. And then specifically, we have this dependence. Okay, this is also a big addition into the tasking model, which consists of being able to express data dependencies between tasks. Okay, we'll see that in the next slides. So let's start with the barrier. So when you use barrier in a parallel region, you actually have a kind of place where all threads synchronize. Okay, it can be actually similar to a join, but they are not actually joining. This is why we don't represent this like this thing where they actually end the parallelism. Okay, we just represent that as a place where they wait together. Okay, wait for all each other. Some constructs actually have an implicit barrier at the end. For instance, this is actually an implicit barrier, but it's obvious because actually we are closing the parallelism. Okay, so you can actually use barrier in order to force the task completion. For example, in this parallel region, I have a master that generates tasks, then I have another barrier, and then I have a master that generates tasks. Okay. So the tricky thing here is that as this is a master, this is not a single, there is no barrier at the end. Okay, but I put the barrier explicitly here. Okay. So if this function is generating tasks like we see here, okay, those tasks will be finished when I exit the barrier. Okay. Actually, the representation is perfect because this barrier is implementing this wall here. Okay. But not actually joining the threads. And then the next set of tasks, the ones created by T2, will only be starting after the barrier. Okay, so the representation is clear because these tasks cannot be mixed with each other. Okay, the barrier puts them on one of the two sides of the wall. Okay, then we have probably the most important directive for waiting, and it is strange to actually explain task wait so late in the lesson, but it's okay. So we have the task wait directive, which implements single level shallow task synchronization. Shallow means only for the children, not for the grandchildren, okay? So it will wait for the completion of child tasks of the current task, okay? Just children, not descendants, not grandchildren. And it includes an implicit task scheduling point, okay? I think we have previously seen this example, no? We have parallel single with an outer task and two inner tasks and a task wait, okay? So we have here the task A, no? It's the red thing, and then orange and green, okay? Green may have an additional two tasks, which are not shown here, okay? But it says children tasks may create additional tasks. And this task wait here is what it is enclosed in the brackets, only waits. So the task wait is executed by task A, and it only waits for B and C, okay? What happens to C1 and C2? They should be weighted by C. Otherwise, they escape the region, okay? Which could be possible, but it's probably not very good, because probably they are doing work that you will need to get. So if they produce some data that you expect to get after the wait, after the task wait, be careful, because unless C has done a task wait for C1 and C2, that data may not be available, okay? So if your parallelism is complex and you don't want to do that, you don't want C to wait, what you can do is use task group, okay? So here what I'm doing is I actually replaced task A by a task group. Task group is not a task. This is why this is round. The tasks are round, but the task group is like regular code, okay? It's not round. But it allows you to actually have a task wait, a deep task wait after the task group. So now the task wait waits for everything, including children, grandchildren, grandchildren. Okay, all of them. Okay, very good. Let me ask if there are any questions regarding the topics that I am currently explaining, or any detail that you wanted to ask. Okay. So now moving to
Hello?
yes,
Yes, we have a question here.
sure.
Sir, what's the difference between private and first private?
Oh yes. Let me go to the example that I had. Maybe not to move here. Let me go to this example here. So for example, let's focus on this private here. Okay, private and first private are the same for parallel or for the tasks. Okay, so if I do private C, I'm only saying I want a copy of C to become private here. It's let's say exactly as if I do, actually it's probably, we should see if it works or not, but it is exactly if I do that and I put that out. Okay, so I get a copy of C with no particular value because it is private. Okay,
Okay.
if I do first private, actually I cannot show that here because it would be something like this, assuming that this variable is this one. Okay, so in first private, I get a private copy, but it is initialized with the value from outside. Okay, so it will become 2 because this variable outside takes the value 2. Okay,
Oh, okay.
so
And if we don't declare
yeah, you Can you hear me?
Yes, now we can
Yes.
hear you.
Yes,
Uh,
there was a network issue, I think.
yeah.
Go ahead.
Uh, so I was asking, if we don't declare C as private or first private, can we access it as a variable inside the parallel region which is shared? As in, if we make any modifications inside the parallel region in C, they will reflect outside the parallel region as well?
Correct. So if I understand your question, you want to have C here,
Yeah.
but you don't want to say private C.
Yeah.
And then because in the parallel, the definition says that any variable is shared, C will become shared both for the parallel here and the task. And you
Oh.
can modify C, and the modification will be seen outside.
Okay. Okay. Thank you, sir.
Okay.
Thank you.
So just because I have that written here, no, I can actually do make run. And I see that now C takes the value 12, while before C didn't change the value. Okay.
Okay. Okay. Okay.
So
Got it. Thank you, sir. Thank you.
you're welcome. So this is the difference between having C as shared now, because there is no specification. So this means that from this point to this point, the variable is the same, okay, compared to do private C, which was the original example, okay, and then you get C as private, so it doesn't get modified, okay? Very good. Any other questions, by the way, now that we are more interactive, maybe? Okay, so I will keep going from the current slide, no? After seeing the task group. So we saw barrier, task weight, task group, and now we do the task dependencies, okay? So this is like the most advanced way of or style of synchronization that we have with tasking, okay? So the idea here was to actually try to relax a little bit more how the tasks are executed, okay? So observe that as far as we are now, the most flexible way of executing was still a little bit structured, no? It's a set of tasks, a barrier, another set of tasks with no relationship between them. So this means that unless you put a barrier or you do some tricky things with particular synchronization variables, you get either tasks executed or you finalize them, no? It's like binary. Tasking, no tasking, okay? So here you get a little bit more of flexibility in the way you actually execute a task graph. So it's not executing a block of tasks, but now you actually can build a graph and then you execute the task graph. Okay. So the clause itself is pretty easy. It's just doing depend on a number of variables. Okay, so we call that task dependencies, but actually what we mean is that we provide the data hints. So we provide hints on the data that is being used on the task. So for each task, we get which data is actually being used, and from there, the runtime system determines if two tasks can be executed in parallel or not. Let's see how we do that. So this is used to compute dependencies, but actually it is not a dependence, although we say depend. Specify the data directionality of a list of variables. Okay, this is why we have this dependent type, because a variable can actually read one variable. This would be an input. A task I don't know if I have said that. A task may actually read a variable, then we have an input. A task may actually write a variable, then we have an output. No? If a task writes a variable, that variable is an output from the task. Or a task can actually read and write the same variable, and then that variable is an in-out, input and output. Okay, so this is actually what we have here. Okay, in, the task only reads; out, the task only writes; in, out, the task reads and writes. And the list items are variables, a named data storage block, memory address, or they can also be array sections, which is pretty interesting, a designated subset of the elements of an array. So in this case, we can say A from a lower point, so the minimum index included in this region, and how many elements. Okay, so one element would be A of 10, 1. Okay, that would be just A of 10. A of 10, 2 would be A of 10 and A of 11. Okay, that's the region. Okay, be careful if you use Fortran, because in Fortran, I think the regions that the language itself is able to express is lower upper. Okay, so you should say A of 10 colon 11. Okay, and then this includes two values, 10 and 11. I think it's like this. You should check the specification. Okay, so if a task does input on a given variable, then the task will depend on all previously generated sibling tasks that reference at least one of the list items in an out or in-out dependence list. Okay, so actually is items in and out or in-out. Yeah, there is a question there.
तो आप इधर पहुंच के फिर आ जाए 1 मिनट। हाँ,
काटने से पहले, काटना नहीं है।
Sorry. Okay, I don't know if there was a question, but apparently it was not. Okay, so if a task does an out or an in-out, then it will depend on both input and out or in-out data types, dependence types. Okay, so basically here is if I have a task or if I have a pair of tasks that does input on the same variable, this is not a dependence because reading is not modifying anything. Okay, but if I have one of the tasks doing an out, then I will have a dependence. Okay, actually the dependencies are exactly the same that we have in superscalar processors. It's the typical read after write, write after read, and write after write. Okay, and here we see the example of a read after write, no, which is probably the usual dependence that one thinks of. So we have a task that does a depend out A, and here this guy will probably modify A in some way, A equals whatever. And here we have depend in A, which means that this guy will do maybe a printf of A, or will do something equals to A plus 1. Okay, so this means that we have the typical task graph that we were having before, but now in this task graph we have an arrow in this direction from B to C. Okay, which is actually represented here. Okay, so we will not execute B in parallel with C because we have this dependence. Okay, so this is actually implementing the task graph that we want to support in this case, which is supporting the dependence, which is read after write. No, this is the read and this is the write. So if we go to the next slide, this is computing dependencies between one writer and n readers. It's the reverse. I have one output of A. This guy will do A equals something. Then we have here two tasks that have an in of A to do various things on the A. And this is the task graph that we are creating here. it's A, which is the enclosing. A is this one. Then we have B, C, and D, which are these ones, okay? And we have this task graph. B actually should be executed first because it has the out, and it actually gets into C and D, okay, because they have the input, okay? So this is two dependencies, read after write, okay? And we may have more. I mean, we can have a list of or even tasks in a loop within A, and we will have plenty of tasks at the bottom and just one at the beginning, okay? Very good. So we can reverse the dependence, in this case doing several readers and one writer, okay? That may happen in an application that actually you just use A for some of the tasks, and at the end you need to modify A maybe for the next part of the program, okay? So in this case, the task graph is the same, but the relationship now is that B and C generate this in-out dependence to D, right? And those are two anti-dependencies. This is also a concept coming from computer architecture, okay? So in the processors, between the instructions, you may have these anti-dependencies, where it's write after read, no? You are writing after reading, okay? And then you can have also the write after write, no? This would be the same code, but this task now is doing A equals something, and this task is also doing A equals something. That may happen in a serial program because you are reusing A for different purposes, okay? So if you want to keep the structure, but you are interested in taskifying because there is more additional work to do, then you just put out A, okay? Which means that the tasks are dependent. B should be executed before, and C afterwards. Why? Because they are actually created in this order, okay? So actually dependencies, so actually the task graph that results out of the dependencies is based, so its structure is based on the order of creation. So tasks created before, if they have any output dependence, it will go before, okay? And subsequent tasks will be those that depend on the particular data, okay? In this case, write after write. Very good. So the depend clause is actually following this structure, okay? We have some restrictions on the list items, okay? And this is set by the specification. List items used in depend clauses of the main task or must indicate identical storage or disjoint storage. And this was actually causing a lot of discussion in the standardization committee, because it was like, let's try to offer the implementations a way to do the implementation easy, okay? Of course, for a generic use of task dependencies, we would like to have any storage indicated in the directive, in the clause. But the problem is that implementing that as any storage is difficult, is very costly actually, okay? So at the committee, we prefer to say the programmer needs to identify which are the objects and refer always to the same type of object, okay? So if it's 10 elements, always 10 elements, not 8, now 8, now 7, now 6, now 10, okay? Don't change the amount of storage referred to by the variables in this list, the variables or the array regions. List items used in dependent clauses cannot be 0 length, okay? So they should at least have one element. And a variable that is part of another variable, this is like a field on a structure, but it is not an array element or an array section, cannot appear in a depend clause. Okay. So this means that, yeah, but actually, I would say that a field, if a field of a structure is an integer, it should appear in the clause, but here it says that do not. Okay. So the important thing is that what you should not do is, for instance, have a depend out on the full array. No, this seems to be A from 0 and n elements, assuming that the array or the definition of n is 100. And then in another task, do from 25 to 50. Okay, because this thing will actually be in the middle of the array. Okay, you are moving the starting point and you are moving the size. Okay, and this is not allowed. You should have this in A from 0 to n. Okay, or you can actually do two tasks here, from 0 to 50 and from 50 to 100, and then here use the same thing, 0 to 50 and 50 to 100. Okay, but you should keep the same partitioning across the use of the dependencies. Okay, so here we have an example of matrix multiply with data dependencies. Okay, so you have a matrix multiply block, which actually multiplies a block of BS by BS elements. Okay, and you implement matrix matmul, assuming that BS divides n perfectly. Okay, on these three variables, A, B, and C. You do parallel single, and then you do the three typical loops of the matrix multiplication, and then you do task depend in the block of A and the block of B, and then in out the block of C. Okay, and you do matmul block with the proper values here, and then you pass this function the block, the current block of A, the current block of B, and the current block of C. Okay, so observe that in the case of the K loop, this in out Cij doesn't depend on K. This means that you have a dependence there. Okay, which is actually represented by this arrow here, assuming you have matrices built on 2 by 2 blocks. Okay, so there will be as it is 2 by 2, this K loop will have two iterations. On the first iteration, it will actually go to C00. On the second iteration, will also go to C00. Okay, so the second iteration will depend on the first one. Then you will move J to J plus BS. Actually, this is a good point, because that would not be 0, 1, but it would be 0 BS. Okay, but it's the same. It's C0 BS and C0 BS. Okay, so it will depend also on each other. Okay, so this way you can actually create one task per block multiplication. Okay, and let the runtime system to organize the scheduling of those tasks. So usually you get good performance doing that. Okay, actually, related also to tasks, we have the task loop. So at some point during the discussions of the task, it was clear in the committee that it would be good to have loops based on tasking. Okay, and the reason is pretty simple. If you have, for instance, an OpenMP application that is using sections. So here I have synthetic phase 1, synthetic phase 2, synthetic phase 3. They are sections. You can actually cannot use for inside of the sections. So this is not allowed. Okay. What it could be allowed is in the sections use task loops. Okay. So in task loop, you also break the loop into chunks, but then every chunk is actually executed by one task. Okay, so how it is this task loop? Task loop with some clauses where the clause is, well, there are some clauses that are actually shared with the word sharings. If, which is already explained, shared, private, first private, last private, and default. This is actually coming from the OpenMP4. Then we can say the grain size or num tasks. So what is the grain size? It would be what is the chunk size for this loop for every task, or how many tasks do we want to create? Okay, it's two different ways of expressing the parallelism. We can collapse, we can do final, priority, untied, and merge. Okay, and we can also do no group related to the task group. Okay. So the grain size is actually used when what you want to express is the work that is worth it to execute in a task. Okay, so you say grain size 10, and this loop will be split in chunks of 10 iterations. So 0 to 10, 10 to 20, 20 to 30, 30 to 40, etc., etc. Okay. The other option is to use num tasks. Okay, in num tasks, we actually say how many tasks we want to create. So if you know that there are a number of threads, you can actually do double of the tasks, for example. You have 5 threads, I'm going to create 10 tasks. It is not good to actually say the numbers here. So I would probably prefer to use grain size, no? Because it's more understandable from the programmer perspective. Okay, but you have the two options in case you want to play with the specification. Okay, and then we have the task group. Okay, we have seen that before related to the task weight. No, this is the deep task weight. Okay, in a task loop there is an implicit task group that encloses all the tasks that are created in the loop. Sorry. You can also use the no group clause in such a way that the tasks will not be weighted at the end. Okay. So in this case, you will not use the task weight, and foo and bar will be able to execute with the tasks coming out of the task loop. Okay, so it will allow to continue the execution of the encountering task without waiting for all the created tasks. Okay, and I think, yeah, we reached the end. So let me know if there are any questions. My plan now is, if we have time, I have a simple application written with for and tasking to compare. So if you want, I can show that, and maybe complete some questions that you may have. Would that be fine? So let me go here. I don't know if you are speaking, but you are muted. Actually, you are muted in Zoom. Yeah,
Yeah, okay.
now I can hear you. Yeah.
Okay, thank you. I think it's very difficult to grasp everything from a very short time.
Sure.
Especially the second half, especially the task loops and the groups, what you have done it, especially after the task intermediate, it's
Yeah.
very difficult to grasp. I just understand the task synchronization up till, but it will be good if you have like a if you can share the slides as well. Plus, if you have the code of all these with us, like small code and small examples that you can share with us,
Yes.
so that we can later on go, because here we just get the hint from you, and with those codes that we later on run, we can learn a lot from that. If that be
Yes.
possible, you can share the codes with us. It will be very good for us
Yes.
with all these tasks.
Yes.
Sure,
Yes. I was also planning to send the codes that I have here. Yeah.
Okay, cheers. Thank you.
You're welcome. So do you want to, do we have time to go a little bit over the Cholesky application?
Yes, we have time.
Yes, okay.
Yeah.
So let's just go here. I have this Cholesky, okay, which I think it's pretty easy to follow. Okay, so let me go to the end and see. So this is the main function here. Okay, so we have the main function. I go to the portions of the application that I think are interesting. We have some initialization of the matrix, some memory allocation. We have the original matrix and the matrix on which we do the computation. We allocate the matrix that is based on blocks. We copy the original matrix to the matrix, and we convert the matrix to blocks, and then we get the number of threads. And here we start the parallelism, okay, parallel and single, okay, and we invoke Cholesky, okay. Then we convert the matrix computed to linear, and we do a check to see that the results are okay, okay. So the important thing here is that we enter Cholesky. Well, actually, this only happens if we have plain tasks or OpenMP tasks, okay? We enter Cholesky already in parallel, okay? If we are using for, we are not having this parallel outside. That's reasonable. But then here I have 4 implementations of Cholesky, okay? We have the supporting functions of Cholesky, basically linear algebra, using usually this uses BLAS. In this case, I think I'm using those functions from the MKL library. Okay, one of the functions is actually matrix multiplication. Okay, it's this dgem. Okay, and then here we have the implementation of Cholesky using OpenMP or OpenMP4, which is probably the same. Okay, so observe that this function has an outer loop that executes OMP, sorry, POTRF, okay? And then it's solving a triangular system, okay? So for each one of the TRSM, we have a parallel 4. This is actually parallel 4, okay? Remember that after a parallel 4, we have a barrier here, okay? And then we have another parallel 4 that implements up to here, doing matrix multiplication and circ. Okay. So another option with the for loops is this one. This one here. You do the same at the beginning. TRSM is based on parallel 4. But then in the second option, you do parallel. You do this loop in parallel, and you just open a 4. Okay. And you actually use schedule dynamic to execute one matrix multiplication in each thread. Okay. You also do no wait, so that the first thread that actually ends executing gem goes to execute circ. Okay. It's a kind of trick to improve a little bit the performance. But the important thing here is the tasks. You can just move from for to tasks in a very similar way. So observe that here I'm exploiting tasks in the OMP TRSM function. Each OMP TRSM is a task. Okay, so this will actually create the tasks as we have seen in the example. But I need to put a task weight here because there are dependencies between this guy and the guys that are written here. Okay, or written or read. Okay, so I need to finish all of them in order to proceed with the next set of tasks. observe that the structure is pretty similar to the one with loops. That was a parallel loop. Now it's a set of tasks that are executed. There was a barrier implicit at the end of the loop. Now there is a task wait. And here we had also a parallel loop, and now we have basically tasks and also a task wait, because there was also a barrier at the end of the loop. Okay. And the last implementation is what we prefer, is the same approach, but now we have tasks with dependencies. I should do, well, only one task wait will be missing. I can actually do that. And probably I can show the full code, right? So observe that with task dependencies, we can actually put the POTRF already in a task with dependencies. This is an in-out on AKK, okay? And this in-out here will actually match with this in here, AHKK, which is this input parameter here, okay? This is probably an input, and this is an in-out, no? AKI, this thing is an in-out, okay? And then I don't need to put a task wait here, because those tasks are with dependencies, and the next tasks that I have here also take dependencies. Actually, observe that from the programmer's perspective, it's very difficult to say that this in-out will match with this in-out here, because actually the index computation is different, okay? They may match or they may not. They may even match with different iterations, no? When k is equals to k and I is equals to I, okay? So this actually builds a nice task graph for Cholesky, okay? And it actually allows you to better overlap the parallelism between different regions, no? Because there are no task waits. Actually, the only task wait that we have here is at the end, at the absolute end of the computation, okay, which is good. So this is a kind of the code that I was expecting to comment a little bit, okay? So I will send you this code. Actually, I have it here. I was doing some experiments yesterday. For example, this was one of the latest, for you to see what is the type of output that we get. No, we get Cholesky with task depths. The matrix is 16K by 16K. The block size is 256 by 256. I'm executing with 1, 4, 8 threads, okay? I'm getting in the order of 50 gigaflops with an execution time of like 30 seconds. And I only check the first one, which should provide successful, okay? And observe that it is scaling pretty well, okay? So from 50 to not 200, but 180. Not 400, but 370, still good enough, okay? 500, 1000, and 1500, nearly 1500. There is a missing data here, because actually the program crashed, okay? So in that particular execution, there was some problem, and I think it's related to GCC. When I compile with GCC, something happens, okay? I have some results already generated. Let me see how results, Cholesky task depends, okay? So in this case, this is an older result that we got, okay, which is pretty similar to what I was showing. 50, 170, 320, 500, 1000, 1500. Okay, in this case, I think that was compiled with the Intel compiler, and we had no issues at the end. Okay. So this is the type of things you can do. Of course, if you have your own application, and you put OpenMP on it, and you have any questions, contact us. I mean, we have a group that can provide some support on annotating applications with OpenMP. Okay, so I guess you will have also a talk with by Antonio Peña, which is also my colleague here at BSc, and he also provides support for this kind of annotations, and also with MPI. Okay. So yeah, I will send these codes to Muhammad Usman so that he can distribute among you.
Okay, thank you very much. Oh, do we have any other question? No? Okay, thank you, Xavi. This is Tasadduk. Nice to see you after a long time.
Thank you. Thank you.
I took your course, I think, 2010 and 11. So I
Ooh.
will share that,
Nice.
in which we wrote Smith-Waterman, I guess, at that time. So
Okay.
I have few questions, and number one, the OpenMP3 GCC 5 and onward has the support of OpenMP3, right?
Yes, yes.
Yes.
Any recent version of GCC will have this support. Yeah.
Yeah. And we are also targeting RISC-V based single board computers. So that computers, Debian has the GCC 7.8 compiler support. So can I assume that the OpenMP support would be also there?
Yes, yes.
Yes. Okay. Then
For
that's fine.
RISC-V, it's also supported.
Yeah. Then we have some applications, real-time application having some complex and irregular pattern. Later, I will share via Usman with you the details of that, and we will try to write that code with your support. And regarding the OpenMP, I saw a lot of details, hardware details are there. Are we moving, our OpenMP is moving towards similar to the like Chisel or hardware description language, are trying to give that kind of support? Because most of the details are related to the like we have in hardware description languages, such kind of details. So do you have any future plan to go towards that kind of languages like Chisel and HLS?
Okay, not that I am aware. It would be actually interesting to see if we can apply some of these ideas of scheduling or tasking onto these more hardware-oriented languages, actually. So yeah, why not? It will be probably a good research topic.
Thank you again. Thank you very much.
You're welcome.
Dr. Chavi, sir, thank you so much. Thank you for your time and presence. We are honored to have you with us. Thank you so much.
Thank you so much for your invitation. It was a pleasure to be with you. Very good. So I disconnect now. Bye-bye.